So just a little bit of a heads up for the rest of the semester. So what we were covering got a little bit off skew from what I was expecting. So a little bit of this is more doubled up than I was hoping for it to be. So definitely, if you have any concerns, let me know. But this week, so we have homework 7. We're going to be going over the Butterworth filter stuff today. So you should be able to do that after this class. Quiz 8 is about Butterworth filters. So usual, just a couple questions. So hopefully that shouldn't take too much time. And then quiz 10 is going to be looking at some stuff we'll be talking about today and also on Thursday. And so since I tried to kind of stagger the homeworks, homework 8 will be due on Wednesday, and then homework 9 is going to be a short one. It's going to be Z transforms. And so that's going to be on the Tuesday, the week of the final exam. So making that do a little bit sooner so I can give you the solutions, give you some time to review that before the final exam on Thursday. So final exam is going to be like what we've done. There will be a take-home portion. The format of the questions might be a little bit different. We're going to try to cascade some of the concepts together, and I'll try to provide some examples of that when we get closer, in addition to going over the practice exam on that Tuesday, like what we've been doing. I'm hoping to get the exam 2 grades to you today. A little bit of a delay with the TAs. I'm going to check in. If I don't hear back, then I'll try and grade those up, get those back to you. So as you can see, we've really only got a couple weeks left, so definitely take a look at LMS. I'll let you know when I post the exam 2 grade so you can see what the estimate is. And if you have any concerns, really this is the week that you should come to me and talk about those. But unfortunately, there's not a whole lot of leeway between the end and exam 2, especially because I need to have all of the final grades in 9 a.m. Monday the following this exam. So I don't have a whole lot of time to play with that either. So if you have any concerns, definitely let me know. And like I said, I'll try to get those to you quickly. And hopefully this is manageable. I know this is that crunch time at the end. So if you have any concerns, then let me know about that as well. All right, so where we left off before the exam is we had this idea that there's these low pass filters that we use in a few different situations, right? So we use them in our communications. We really use them in sampling for reconstructing signals, right? Isolating specific frequency ranges that we're interested in. And so what we found is that this ideal low pass filter in reality is not actually something that we can implement, right? So our ideal low pass filter, what we had, right, for now, look at cutoff frequency of 1 here, magnitude of 1, right? So we had something like this was our ideal low pass filter. So everything within our band of interest is going to pass through unchanged. Everything outside of that, we're going to completely get rid of. And so we said that in reality, we can't actually implement this. So what we want is some kind of approximation. And so this led us to this idea of Butterworth filters, right? So not the only type of approximation filter that we can have, but this is the one that we'll look at to get a rough idea of how this might work for this class. And so what we found is that if you take something like an RC circuit, that your response is actually going to look something like that, right? So it's not an ideal low pass filter, but there's certain things that we can control to make it a decent approximation. And so what we can do, we can say at omega equals 0, the magnitude of this filter should be 1, right? Because that will match up with this ideal low pass filter, right? We can always scale if we need to, but we're going to just, for the purposes of looking at how we would design these filters, have a band pass of 1. Okay, so the other thing we said is that at our cutoff frequencies, so in this case, for our first run, we're just using omega c as 1. We want that to be at minus 3 dB point. right? And so what we're saying is that if we go past here, right, it's going to be more than a 3 dB reduction in the frequencies that pass through. We're going to say that's probably a close enough approximation for what we want our filter to do, right? So there's going to be some residue out here, but it's attenuated enough that we're not worried about it. And so what we found from our equations when we were trying to solve for coefficients of a specific form is that we have some additional things that we can play with, right? So even just pinning these down, there's still some that we can mess around with to try and get even closer to this ideal. And so what we said is that we also want to be maximally flat at omega equals 0, right? So in this region here, we want it to be as flat as possible. And so because this is flatter, then we're going to have a wider range where we pass through at very close to 1. And so we went through and we found some derivations. So what we had used was an expression for the magnitude squared, because we found our constraints on the magnitude, we could relate to the magnitude squared, and turned out the math was a little bit nicer for us to do that. And so what we were looking at for our case, so previously we had a third order case that we were looking at. And what we ended up with was a form like this, right? So we had started off with an omega 6, 4, and 2 in here as well. And then we found by this maximally flat that some of those coefficients went to 0. And so we were left with a form like this. And so what we ultimately want to do is we want to get to this Butterworth filter. And so to do that, we need to figure out where the poles are of our transfer function. So when we were deriving this, we had used this idea of having our Butterworth filter, and we also used this symmetry to get to these nice equations. And we can relate that to our Laplace transform as well. And so what this means is that when we're looking at this form, we're actually going to have some poles which are related to our Butterworth and some poles which are related to this mirroring that we used to get the form that we wanted. Right, so to do this, we want everything to be in the Laplace domain for finding the poles. So we're going to find that's the easiest way for us to look at stability of our poles that we're looking at. So we want to convert this frequency response into this Laplace domain. So to do that, what we said is that if you have a frequency response like this, right, a Fourier transform, then you can substitute S for j omega. So what that means is that we need to get a j in here somewhere. And so if we substitute in j omega into this omega, then we actually end up getting a minus sign to account for all the multiplications of j that we have added in here. And then once I have it in this form, then I can substitute in S for j omega. And so this is equal to that B of S, B of minus S. So this B of S here is our actual Butterworth filter transfer function. And so since this is something that we want to actually implement, we want this to be stable. And so what we're going to find is that when we're looking at the poles of this transfer function here, that we're going to get 3 poles which are stable and 3 poles which are unstable. Right, and so these just came about from using this expression to find the form that we wanted. And so what we can do is we can throw out all the unstable poles, and we're going to keep the stable poles from here to form this Butterworth filter transfer function. right? So for this case, we have our poles satisfy 1 minus s to the 6 equals 0, or in other words, s to the 6 is equal to 1. Right, so it turns out that there's going to be 6 possible poles here, right? So what we're actually going to do to try and figure out what those 6 poles are is we're going to rewrite a couple of things. I'm going to let my S be written in polar form. All right, so this is going to make doing the math a little bit easier having it in this format here. And so then I have R to the 6, E to the J 6 theta is equal to. And so now to get all of the possible solutions that I can have for this, what I'm actually going to do is I'm going to rewrite my 1 in polar form as well. And what I can recognize is that I can write my 1 in this form. Right, so as long as k is an integer, this is always going to be equal to 1. Right, so I can have e to the j 0, e to the j 2 pi, 3 pi, right? Substitute in 3, then you have 6 pi, so on and so forth, right? So what this allows me to do is now I can equate my magnitude, and I can equate my phase and get expressions for that magnitude r and that phase theta that define my poles s. Okay, so from this comparison here, we have r to the 6 is equal to 1. So what we're going to get here is r equals 1. And then for the other expression, we have 6 theta is equal to 2 pi k. So from here, we get that theta is equal to 1/3 pi k. All right, so let's visualize what these poles look like. All right, so we're going to look at our real imaginary plane here. So what this part here tells us is that the magnitude of all the poles is 1. So what that means is that all of our poles are going to be on the unit circle. Right, so this is something that we're going to see anytime that we have this omega c is equal to 1 when we're looking for these poles, that they're all going to end up on this unit circle with this magnitude of 1. So now if we look at the theta, right, so if you recall, we're expressing in polar form, right, the r tells us the magnitude, and then theta tells us this angle here. So when k is equal to 0, we have theta is 0. So we have a pole at this location. And then when k is 1, so we have pi over 3. Right, and then k is 2, we increase by another pi over 3. When it's 3, then we have pi. And we keep increasing as we go around the circle. And then what we find is that once we get to, in this case, k equals 6, then we're back at our original, right? So we only have these 6 individual poles. At that point, we start just looping around those same ones that we already had. Right, so now we have 6 poles here, right? So these poles satisfy S, our R is 1, then we have E to the J pi over 3K. And so what we want to do is we want to choose out of these 6, the 3 which are stable poles. Right, so if you recall when we were talking about stability for our systems, we said that for our physical systems, we're looking at causal systems. And so in that case, what that means is that our H of t, that impulse response, is going to be right-sided. And so what that also means is that our region of convergence is also going to be right-sided as well. And so for our system to be stable, then the ROC of our Laplace needs to include this imaginary axis. Or in other words, since it's right-sided, all of the poles need to be on this left side. Okay? So what that means then is that these three here are those stable poles. Right? So we have three that are stable, three that are unstable. Right? So these three are that P minus S. These three is the Butterworth filter. So what that means then is that we choose the poles, which are E to the 2 pi over 3j minus 1 and E. And so one thing is that you could go in either direction, right? So you could go plus 2, 3, 4, right? Or you could go backwards direction as well. What's nice about here is that you'll see some cancellation when you do the substitutions in there. But you do tend to have this nice symmetry of a positive, negative pole like that. And so now if I want to form my B of S, so what we know for our transfer functions is that if we have a pole at a certain location, then those are the values for which when S is equal to that, we're going to have division by 0. So we'll take this one since that's a little bit easier to look at. So when S equals minus 1, then we're going to have a division by 0. So the way that we capture that is having an S plus 1. Right, so now if I substituted this pole in here, we'd have a division by 0. Right, so it is indeed a pole. Now similarly with these two, we have S minus E to the 2 over 3 pi j. Right, so if we substitute that in there, we have division by 0. Right, so definitely an easy part to miss when you're substituting it back into the transfer function is that you are going to have an additional minus sign for whatever those poles are. And then substituting in, we also have our minus, like so. And so now if I was to multiply this out, I can reduce it down a little bit and get S cubed 2S squared 2S plus 1. All right, so all this derivation we did for a specific order that we wanted. Right, so we started off with this idea that we wanted something which was a cubic in the denominator. Right, so something that was a third order transfer function. And then from there, we had formed this idea of the magnitude of the response. And then we used that magnitude to figure out, right, here's all the constraints that I want. What form am I going to end up with? And so we ended up with something like this, which captured both this B of S that we wanted and also had some residue that we used for computation. And so from here, we can solve for the poles of this transfer function. We realize that some of those are stable, some are unstable. And so we throw out all these unstable poles, keep the three that give us the form that we're actually interested in. Right, that actually gives us this third order transfer function that we originally want. All right, so that was for one specific case. We can expand this idea to additional orders. So in general, when we're designing our low pass Butterworth filter. And we're going to do the design with our cutoff frequency of 1. What we'll see in a second is that once we have that result, it's very easy for us to just change the cutoff frequency from this result that we had before. So in general, what we're going to end up with is this B j omega magnitude squared is going to be of the form 1 over omega to the 2n plus 1. And so to get that back into the S form, I want to also note that n, right, so I wrote it as 2n, that n is our filter order. Right, so like in this case, I wanted a 3rd order filter. And so if we look up here, right, I ended up with 2n is 6 in that expression. All right, so to get to B of S that we're interested in, so B j omega squared, I want to substitute in j omega where I have the omega. And by doing that, I'm going to end up with some -1s in there. Right, so this is my B j omega, B minus j omega. And so if I want my S form, then I'm just going to substitute S in for j omega. And so what we get, and you'll see this in your reference tables towards the end, is that this B of S, B of minus S, is going to have the form 1 over -1 to the n, S to the 2n plus 1. Right, so you're going to have, depending on what your order is, right, if you want a 3rd order, then you're going to have -1 to the 3rd, S to the 6th plus 1. So then, as I said before, the poles of B of S are chosen from the roots where this -1 n S to the 2n plus 1 equals 0. And you're going to choose the ones that lie in the left half plane. Or another way to think about it is the ones that have negative real parts. And a little bit later, we'll take a look at another example. Right, but first I also wanted to say some of the things that we can do once we have this Butterworth filter. Right, so this process here, this is going to give us a Butterworth filter which has a cutoff frequency of 1. Right, so it makes sense that there's probably a lot of times where we don't actually want a cutoff frequency of 1, right? There's some other cutoff frequency that we're looking for. And so what we can do, if we want a Butterworth low pass filter, and we want it with some other cutoff frequency omega c, well, if our Butterworth filter that we have, the magnitude response, we're going to have 1 over square root of 2, that roughly dB point. And so in our original Butterworth, have a cutoff of 1. All right, so we have something like that. And now what we want is something which is very similar, except now we have some arbitrary cutoff frequency, but we still want at 0 our height to be 1, and at our cutoff to have that -3 dB point. So what we can tell by looking at this is that really all this one is the same exact Butterworth that we had, except we've scaled the frequency, right? So if omega c is less than 1, then all we need to do is just squeeze this to get the right omega c, right? If it's larger, then we expand it appropriately to get this point to be wherever that is, right? The shape is the same, it's just the scaling here that's different. So what we're using is scaling in the frequency domain. And so your H here is going to be just like your original Butterworth, except you're going to substitute over omega c. All right, so equivalently, if we were looking in the Laplace domain, right, you're just substituting where you had S before, now you have S over omega c. All right, so that's why we did everything with respect to the cutoff frequency of 1, because then once you have that result, then any cutoff frequencies that you want, you can just make this substitution in there. So what actually happens then when you have a different cutoff frequency like this? Well, if we take a look at what happens to the poles here, what's actually interesting, okay, so now we're substituting where we had omega, now we have this omega c, and we multiply top and bottom by this omega c here. All right, so same kind of idea like what we had before. Now we just have this additional factor where before we had 1. And so what this means is when you look at the Laplace domain, is that before where we had all the poles equal to 1 here, right? So now we instead have this omega c to the 2n. And so what you would actually see if you solve for this denominator here is if your original, right? So we have our unit circle here. Right, so our original Butterworth filter, let's say that you had a second order. Right, so maybe you have poles like this. What you would have is instead of everything being on the unit circle, you would instead have everything on a circle with radius omega c. Right, so what your new cutoff frequency is. So what's interesting is that the angles are actually the same. They just get stretched out different color. Because they're just going to be stretched out to this outside circle like so. All right, so turns out that it's actually pretty similar process. So even if you did the substitution beforehand, right, and so you actually looked at this form to try to figure out the poles, the process would still be the same. You're still going to get, in this case, since it's a second order, 2 stable, 2 unstable, you just basically have a different magnitude that you're looking at. And it turns out that we can also use this Butterworth low pass design to get bandpass filters as well. Right, so we saw a couple of times where you might want to use a bandpass for something like the frequency multiplexing. And so again, we have used this ideal bandpass filter, which has those nice sharp edges, which are things that we can't actually realize. But what we can do is if we have our B of S, right, so that Butterworth with omega C equal to 1, that's a low pass filter, we could take that result, and from it, we can generate a bandpass filter. Right, so let's say in my bandpass filter then, we're going to have a low cutoff and a high cutoff. And we have our center frequency. And this is mirrored on the other side as well. So at the center frequency, we essentially want it to be a passband, right? So same as what we saw for our low pass filter. We want that magnitude to be 1 at this point here. And then cutoffs, we're going to use the same value. So we have our low cutoff and our high cutoff. And the shape is going to look pretty similar to what we had for the low pass. Right, but now instead of it being centered at omega equals 0, so we're keeping only the low frequencies, now we're keeping the frequencies that are just on either side of the center frequency, omega 0. And so we can relate these numbers to each other. So omega 0 is actually the square root. Omega L, omega H is a geometric mean to get an average value between the high and low cutoff frequency. And this we typically call the center frequency. And then another thing that we might be interested in is what is the bandwidth of our filter. And so that's going to be the high minus the low. Right, so you could define the high-low cutoff frequency, or you could say, here's my center frequency and here's the bandwidth that I want. And you could get the other values as you need from these expressions. Right, so I'm going to first say that if we have a low pass cutoff, 1 radian per second, right, so our low pass filter, I'm going to write this as B sub L, and instead of S, I'm going to put P for now, right? So just to make it a little bit clearer when I say what we're substituting in. So same form, like if we had, right, so we had something like this. I'm just saying that instead of having S here, we're going to have P, right? So it makes it a little clearer when we do the substitution. So if you have this low pass filter with the cutoff frequency of 1, defined in this way, then what we can do is we can use a transformation where we substitute in for P S squared plus omega 0 squared over omega B S. All right, so what we're going to see is that it turns out that the algebra then gets a little bit messy, but this is a way that if you have this low pass filter design, you want to turn it into a band pass filter. It turns out that you can do this relatively easily, at least conceptually, by just making this substitution. So if we had, for example, here, we want to design a bandpass. And this bandpass is going to have a center frequency of 5 radians per second and a bandwidth of 2. And I want to do this using our third order low pass. All right, so our third order low pass, we use this notation, was we had S cubed. I said I'm substituting in P, so maybe it's a little bit cleaner to look at, plus 2P squared plus 2P plus 1. All right, so that was our third order low pass filter with a cutoff of 1. And so now to get this bandpass filter, I'm going to substitute in for P, this S squared plus omega 0 squared is 25. Our omega B is 2. And so then I can get my bandpass filter. All right, so you can see that everywhere that we had the P, we're substituting in this big expression that we have. All right, so definitely not nice looking. All right, so maybe, depending on personal preference, maybe we could take, so everything is actually S in the top and bottom. So take this 2S cubed here and multiply top and bottom by that. All right, so a lot of really messy algebra going on here. And so probably what you'd want to use more so is something like MATLAB, where you can actually substitute in a symbolic expression and you can have it reduce it down to polynomials in S. So you don't have to do all that by hand. But this is the main idea, is that once you have low pass filter design, right? So we do that initial that we did before, you get some B of S of a certain order. And then if you want a different cutoff frequency, well, you just substitute in S over omega C. If you want a band pass, a little bit more involved what you have to substitute in there. But once you do that substitution, what you would get is a band pass filter, which matches the form here. All right, so let's go back and look at a filter design problem. So let's say that I want to design a second order low pass filter with a cutoff frequency of 1. Right, so first thing I do is I write down my form. So we have B of S, B of minus S is equal to 1 minus 1 to the n, S to the 2n plus 1. And so for this case, I'm looking for a second order filter. And so I'm going to substitute in for n2. We're substituting in n equals 2. So we get 1 over S to the 4th plus 1. All right, so now that I have this form, the next step that I do is I look for all of the possible poles of this transfer function. So the poles here are going to satisfy S to the 4th equal minus 1. right? So you already noticed that this is a little bit different from what we saw with the third order, right? With the third order, we had s cubed equals to positive 1, right? So when we put this into polar form, we need to keep that in mind, that the form that we used before is not going to work exactly for this, right? So we're going to let s be written in polar form, right? That part doesn't change. We did previously when we had 1 was we wrote our s in the form, or wrote that 1 in the form of 1 e to the j 2 pi k, right? But now we have a negative 1. So our magnitude, when we're writing in polar form, is always going to be positive. So to capture that minus sign, we need to do that in this exponential part. And so the way that we can capture that, we're going to let minus 1 then be defined. Magnitude there is 1. And then e to the j. So if we just had this single minus 1, then we could capture that instead of e to the j 0 like we had for 1, it would be e to the j pi, right? But that only gives us one possible solution for this theta, and we want to be able to get all of the ones on that unit circle. So what we can recognize is that if I add any multiple of 2 pi, I'm going to get back to that same minus 1. Right, so when k equals 0, we have j pi. When k equals 1, we're going to rotate a 2 pi. Right, k equals 2, we're just going to keep rotating and get back to this minus 1. But by having this integer k in here, that gives us the ability to find all the possibilities on that unit circle. I'll make a note again here that our k is an integer. Right, so if I do these substitutions in, so we substitute in our s, we're going to get r4 ej 4 theta is equal to 1 e to the j pi plus 2 pi. So once again, we can equate, so our magnitude here, r to the 4th equals 1, gives us r equals 1. And then we have for theta is equal to pi plus 2 pi k. So we get theta is equal to pi over 4 plus k pi over 4. Right, so now this gives us expressions where we can find all of the 4 poles here. But what we know is that 2 of the poles are what we're actually interested in. 2 are going to be unstable poles. So the easiest way to figure out which ones we want to pull is probably by looking at the sketch of the poles. So we know based on R, everything is going to be on the unit circle. And now when K is equal to 0, we have pi over 4. And then we're going to add a pi over 2. Add another pi over 2. Add another pi over 2. And then we're back to repeating those poles. And so now to form our B of S, of those 4, we take the 2 which are stable. So these 2 over here are the poles that I'm going to pull to form my B of S. So we have our stable poles are E, J, 3 pi over 4, E minus J, 3 pi over 4. And so I substitute in for B of S, keeping in mind that we need that minus sign before the pole. So that when we substitute in the pole value, we actually do get division by 0. Like so. And then if I do the multiplication out, what you would see is that you can take this, and you might see something that looks kind of like a cosine. You can substitute values, things like that. What we end up getting is an s squared square root of 2s plus 1. Right, so once I had this form, then I can do additional things, right? So let's say I wanted, now instead, a low pass filter, but with a different cutoff frequency. Well, what I'm going to do is I'm going to sub in for s over omega c, s over 4 in this case. So what we'd have instead is s over 4 squared, square root of 2, s over 4 plus 1. Like so. And now we have a low pass filter with a different cutoff frequency. And if I wanted, say, a band pass, and let's say I know the lower cutoff I want to be 1, the higher cutoff to be 3. Well, the form that we had for our substitution used omega 0 and omega b, right? The bandwidth and the cutoff frequency. But we can get those values from our low and high cutoffs. So we have omega 0 square root omega L omega H gives us square root of 3. Our bandwidth is the high minus the low cutoffs. It's going to be 2. And so to get this filter, what we're going to do is we're going to substitute in s squared plus omega 0 squared over omega bs, which for this case, our omega 0 squared is 3, omega b is 2. All right, so we make this substitution into our original b of s that we have up here. So we have 1 over s squared plus 3 over 2s squared. And then we could do a little bit of manipulation, algebra reduction. Like so. All right, so the key point is really figuring out what that original low pass Butterworth filter is, and then you can get these other types of forms directly from that. And so if you actually look up, say, Butterworth filter on something like Wikipedia, what you would see is for different filter orders, what these coefficients are that you would expect to see in the transfer function. And so from here, you can see where those are actually coming from, what that form is that gets us to these coefficients. Really, it comes down to this idea of making sure that we have stable poles that give us an approximation of the ideal low pass filter that we want. And that Butterworth filter is going to be maximally flat at omega equals 0 and have a cutoff of around minus 3 dB. As I said, there's other approximations that prioritize other features to try and get closer to the filter design that you want. But for purposes of this class, we're just looking at the Butterworth filter. Another thing that you'll notice is if you look at the response magnitude, as you increase the filter order, right? So if you compare the second order, say, to this third order that we looked at back here, right? So comparing the second and this third order, if you look at the frequency response, what you would find is that this edge here is going to become sharper as you increase the order number, right? So instead of being this nice gradual, you're going to have more flat region here, which is going to cause this to drop off more sharply as you increase the filter order, right? So that's why you see those different ones. Of course, how to actually implement them depends on what you have available to you as far as circuit elements go. So let's take a look at a possible circuit implementation here. Right, so let's say that I want to implement a third order Butterworth low pass. And I want it to have a cutoff of 2. And the circuit that I'm going to use, we have our input voltage here. We have a resistor, capacitor, an inductor, and another capacitor. And my output is across the second capacitor. And so the process here, first I want to figure out what will my Butterworth transfer function look like. Right, so that would be my desired transfer function. And then we're going to look at what is the transfer function of the circuit. And then what you do is you just compare the coefficients. And from there you can figure out what do I need all these circuit elements to be to get that Butterworth filter that I want. Right, so we had already seen our Butterworth filter when omega c is equal to 1. Right, so for that we had s cubed 2s squared plus 2s plus 1, right? We already solved for that before. And so now if I want a different cutoff frequency, then we just substitute into that expression. And we're going to get 1 over 1/8 s cubed, 1/2 s squared plus s plus 1. All right, so now we have our desired transfer function. So let's take a look at the circuit itself. And typically the easiest way to do this is to actually convert everything into the Laplace domain. So my x of t becomes x of s. The equivalent impedance for a resistor is just a resistor. The Laplace domain R stays R. Our capacitors are going to become 1 over S times the capacitance. And so this equivalent impedance basically captures that current voltage relationship. Our inductor becomes inductance times S. We have another capacitor here. And then we have our output. All right, so I'm going to define some currents here to help me out. So we're going to have current 1 going through here, current 2, and current 3. Right, so to find the transfer function, I'm going to use some different relationships. I'm going to use a loop equation going around this loop. You get x of s r I1 plus 1 over sc1 I2. I'll call this equation 1. I'm going to do another loop around here. And with a little bit of cleanup, we're going to get y of s, 1 over sc1, I2, SL, I3. All right, so we have still a lot of unknowns here that we need to solve for. So we're going to look for some more equations. I'm going to use a node equation here. So looking at the current going in equals the current going out. We have a relationship between each of these currents that we use. That's 3. All right, so still not enough to capture everything that we need. So we're also going to use a component equation. We're going to look at this capacitor here. We have a relationship between that current and that voltage. All right, so now to actually get everything, right, we need to get everything in terms of y, x, and just those component values. So I'm going to kind of skip some of the details, but we can substitute 4 into 3, and we'll get an expression here. And then I can take this result and substitute that into 1. Right, and then I can also manipulate 4 a little bit and substitute into 2. And do some maneuvering around. And then once I get to this point, right, so now we can see that we have this in terms of I2, now we have an I2. This is all just in terms of y, so we can do a final substituting 7 into 6. And it looks a little bit messy here. Right, so what we're ultimately interested in is that this B of S that we derived, that's our transfer function that we want for our circuit. So from here, we're going to solve for the transfer function of the circuit itself. So the transfer function is the output over the input. And so a lot of algebra later, we get that. And so now, to figure out what I need for all of these circuit element values, all the resistance, inductance, and capacitances, I'm going to take these coefficients here and compare to the form that I want up there. So what we're going to need is R LC1 C2 equals 1/8. LC2 is 1/2. And R C1 plus C2 is equal to 1. All right, so one thing that we notice here is that we end up with 3 equations and 4 unknowns. So there's actually multiple possible solutions So what we do is maybe fix one of the values, and then from there we can solve for the other coefficients that we're looking for. Something you might be interested to know is that you can actually do this kind of solution very easily using MATLAB. Right, so what you can do, I don't know if there's a way I can make this bigger, but we can define the symbolic variables that we're looking for. Okay, so we have our resistance, inductance, and the two capacitances. So what this positive here tells it that when it's doing the solving of this, that those values can only be positive numbers. Right, so anytime that you're doing symbolic expressions, you can provide some constraints. So you could say, well, it needs to be a real value, it needs to be negative, positive, things like that, and it'll restrict the possible solution that it gives you. And then from there, what you can do, you can use this solve expression. And so the way that we're doing this is in this first part, right? So we have here, these are the values of our equation. Minimize for a second, right? We're taking these values here, and we're making those into a vector, and we want this vector to be equal to, and then we're going to provide these symbolic expressions as a vector on the other side. So we'd have the first 1/8 equals this expression, right? Go down, the next value of the vector, we have 1/2 equals this, so on and so forth for however many expressions that you need. And then you want that side to be equal to, double equal sign is a way to express that you're doing a solving here, not a assignment. And what you would see is that it actually gives you a relationship of each of those variables with respect to what we would consider a free variable, right? So in this case, if I was to substitute in a vector C2, then I could get C1, L, and R. Right, so we didn't tell it what our free variable was, so it just kind of picks one. If you wanted to look, say, in terms of L, right, so maybe that's the one that you have some freedom to define, or maybe you have some constraint there. So what the second argument here is doing is it's telling the solver to say, I want you to solve for C1 and C2 and R. Anything else is going to leave as a free variable. And now you can see we have these same expressions now all solved for in terms of L. And then if you had, say, a specific value of L that you were interested in, there's a sub plan. Right, so this subs here allows you to take a symbolic expression, which is this first argument, and you're saying in that expression, everywhere I have an L, I want you to substitute in the value of 1. And so when you do that, it's going to give you resulting values for each of those other terms in your expression. Right, so turned out it's actually a little bit easier to use something like this, especially if you have a ton of these symbolic expressions that you're solving for, right? A nice little handy shortcut to get to those values. Right, so a little bit of an aside there. And that pretty much wraps up then everything for Butterworth filters, right? So you might see in homework or exam this kind of idea of you have some circuit, gives you some specific form, and you want to figure out what is your low pass filter, potentially with an arbitrary cutoff. And then once you have this form and you have this form, then all it is a coefficient matching to figure out what values would I need for these components to get the type of low pass filter that I want. So this is one application of the Laplace transform, right? So similar when we looked at other transforms, we saw with the Fourier transform that we could apply it to communication systems, Turns out it was also very useful for sampling as well. So for Laplace, Butterworth filter design is one possible application, right? So the main advantage there is being able to look at this idea of the poles, right? So we have that concept of stability of this transfer function. And by getting it into the Laplace domain, we're able to take a look at those poles and form a transfer function, which gives us the type of frequency response that we want. Another big application area for Laplace transform is for control systems, right? So specifically what we're going to do is we're going to look at feedback systems. So let's take a look at hopefully a kind of realistic type of system, see where we might want to use something like this. So we're going to take a look at a DC motor servo. All right, so we're going to break this down into a bunch of different kind of subsystems. So we have our DC motor. All right, so we can describe this with a voltage. There's a resistance, an inductance, and then there's also this back EMF if we want more of a realistic type of DC motor. And we're going to have a current going through here as well. Right, so I can capture the relationship between the current and this voltage for this motor. If I put everything into the Laplace domain, I can get the transfer function. Call this 1. So the current is the voltage difference across the impedance. Right, so this captures the input-output relationship of that DC motor. And I can also, another way that I can express this is by drawing a block diagram. Right, so with block diagrams, we typically have our input come in. Right, so we're going to have, this is a summation block, a minus on the V of S. Right, so we capture this top part here. And since we have multiplication here in the Laplace domain, that's going to be that result passing through that transfer function. That's the way that we capture, have something passing through. In the frequency domain, it's multiplication, right? Time domain, it was convolution. And so once we do that multiplication, then you have an output of the current. Right, so I'm drawing it like this because then we'll be able to see is that I can take all of these subsystems and put these little block diagrams together and get an idea of what the overall system looks like. All right, so the next part, if we look on the mechanical side, we have a torque, which is generated by the motor. We'll call this torque tau. And this torque that's generated is related to the current of the motor. Let's call this expression 2. And this K here is just the motor torque constant. Okay. So this block diagram would look like I of S gets scaled by K, produces this torque tau. Right? And so now, what we might be interested in is then what is the position of this motor, right? So we have some voltage going in, it generates some current, this current generates some torque, and this torque is going to generate some position. So how we can capture that, right? So our DC motor, something like this, we're going to have a torque which is applied, it's going to generate some position theta. And so the ways that the motor torque is related to the position right? So it's kind of like in physics 1, right? You have mass times acceleration equals applied force. So this is the angular equivalent. So instead of mass, what we're going to have is inertia, right? And instead of linear acceleration, now we have angular acceleration because theta is an angular position. And instead of force, we're going to have torques. And the net torque is going to be some applied torque. And then we could also have potentially a little bit of friction acting on our motor as well. All right, so this would be our friction coefficient. And this whole thing here captures some viscous friction torque. All right, so we're actually capturing a pretty complex system by doing it this way. All right, so now we have this differential equation, right? I want to get everything so I can keep cascading all of this together. So I'm going to take this expression and convert it into the Laplace domain. So J is just a constant. We have a second derivative, so we have an S squared equals tau. And then first derivative, we have S like so. Right, so from there, I want to bring my thetas all to the same side. And then I can get what is my output theta depending on that input torque tau. Right, so now we have yet another component here. So we have this torque is passing through this expression here, this transfer function. So we're turning our torque into a motor position. Right, and then one last component. So the back EMF actually captures a little bit of back voltage from the movement of the motor itself. And so that EMF is the electromotive force. All right, so putting this differential equation into the Laplace domain, right, so we have V of S, K, EMF, S, theta S. Or in block diagram form, like so. Right, so what's nice about this is now I can express everything in one single block diagram. Right, so if I was to start, say, from here, right, now I have, well, this V of S plugs into there, right, and I have a theta, well, this plugs into the theta, and the tau connects back to the current. And so if I do all of that substitution in, I can get one single block diagram that represents my entire motor. So it's going to capture that this original part here, that DC motor, the mechanical side, also going to capture that back EMF, everything that's going on there. So our combined block diagram, we're going to have our input voltage. And then from that voltage, we can produce a current in our motor. And then that current is going to result in a torque. And that torque is going to result in a position of our motor. But that position is also going to have some influence based on the velocity that affects the voltage going in and generating that current. All right, so just kind of piecing together all those individual block diagrams that we were working. So it still looks a little bit messy, but if you recall when we were first talking about block diagrams, we said that when we have these block diagrams arranged in a certain way, we can combine them together to make a simpler looking system. And so what we can do is we can reduce this by recognizing that when you have these systems cascaded together like this, that the result is the same as just taking that input and passing it through the multiplication of those individual subsystem transfer functions. Right, so kind of pulling on that idea, right, how we looked before. Right, if you have something like that, say y is out here, z is here, right? So we know that z is h1 convolved with x, and that y h2 involved with z is h2 involved with h1 involved with x. All right, so that's what happens in the time domain. We have this convolution. So in the frequency domain, you could express this as h1 times h2, because our convolution in time becomes multiplication in frequency. And so that's what I'm doing here, is that we can see that we have this input feeds into one, feeds into the next, into the next. So I can reduce this down. Instead of having three separate transfer functions, I can combine them together into one single transfer function. And it turns out that I can actually reduce this a little bit further. And so this comes to what I led with, the description here, is a feedback. Right, so we call it a feedback because you have this output, it is feeding back towards the input or further back into this system that we have represented. And so we can take, if we have something that looks like this, we can reduce it to a single transfer function. Right, so here we have two separate ones. So if we look at the generic case, right, so let's say I have an x of s and we'll call the output of the summation E of S. And that might make sense when we're talking a little bit later, looking at these types of systems. So we have one transfer function that is in what we would call this is the feed forward loop, right? So we're going from the input towards the output, feeding forward. And then we have another transfer function here we call our feedback loop. And one key point here, right, we're going to have this be a negative feedback loop. There are cases where you have a positive, negative tends to be more prevalent. And so the main thing is that you'll notice a sign difference in your reduction if you have a plus instead of a minus there. All right, so let's figure out what would this look like. Well, we know our y of s is g of s, e of s. All right, so we get that output by this passing through that transfer function. Our e of s, we make a substitution there. We know is the difference here. We have x of s minus h of s. And what's passing through h of s is y of s. All right, so I can expand this out. G of s, x of s minus g h y. All right, so now if I get all the y terms to the same side, I have 1 plus g h y is equal to g x. And so if I wanted to represent this system here with one single transfer function, then I get my output related to my input, and I get g of s 1 plus g h. All right, so I can take this block diagram here, and this is the same as just passing through this single transfer function like so. All right, so one thing to note, right, so we had a minus sign here. Notice that we have a plus sign in the denominator there. All right, so if you don't remember this form, right, you can always do this solution here. Or if you happen to remember this, then anytime you see something that looks like that, then you can just take and do this substitution here. All right, so if we go back to what we have here then. So for our case, what we have is that feed forward part, G, is that K R plus SL, K S squared plus BS, and the feedback H is like so. All right, so here we're just comparing what we have up here to the form that we have there. And so then I can take and substitute in directly for this. And so I get my motor position related to the applied voltage to the motor. All right, so it's going to get a little bit messy here, which is an unfortunate consequence whenever we have these feedback loops. All right, so what I want to do is I want to get it into just a polynomial on top and bottom in terms of s. So I'm going to multiply top and bottom by this denominator here, do a little bit of algebra reduction, and we're going to get JL S cubed our JLB S squared, and then R B K AEMF So now we have a transfer function, which represents our motor here. Right, so we actually have a lot of interesting dynamics which is going on, right? We have some friction, we have motor inertias, all that kind of stuff that we've captured here. And so in our usual wisdom, when we're really just more interested in what we can learn from this kind of expression, we're just going to take all of these coefficients here. And we're just going to set them equal to 1. Right. So just so we don't have to mess with a whole bunch of additional factors in there. So if we do that, what we get? Theta s, u of s, 1 over s cubed plus 2s squared plus 2s. And so one thing that we've learned with transfer functions like this is that something we're really interested in is looking at the poles of the transfer function. So if we rewrite this just a little bit, so we have s squared plus 2s plus 2, then the poles that I have here are 0, and then quadratic formula gives us -1 plus minus. Okay. So an interesting thing that this tells us, right, if we recall looking at our poles before, is that these poles are stable because we have a negative real part, so that's fine. But since we have a pole at 0, what that means is our DC motor input-output system is not bistable. Right, so this kind of makes sense. If you apply a constant voltage to your motor, then your position is going to be unbounded, right? It's just going to keep rotating without any stopping. And so we can see that, yes, indeed, does kind of make sense intuitionally. Now we can see that looking at this Laplace transform, the transfer function here, and this idea of the poles, that we can verify that using this method as well, that because we have this pole at 0, that this motor is actually not bistable. And so where we'll pick up with next time is we're going to take a look at, let's say that what we want to do is we want to regulate our position, and we want to do this so that we track some reference. Right, so this is our desired reference position. And so what we're going to take a look at next time is, let's say that I just take a very simple feedback controller. All right, so let's say that our voltage that we apply to the motor is going to be based off of the difference between where we want the motor to be and where it actually is. Right, so if you've done anything with controls, this would be a proportional control. Right, so C is going to be our proportional gain, and we're going to want to tune, right, choose that value in such a way that we can satisfy some conditions. Right, so we're pretty close to the end. We'll start with that next time. Is what we're going to do is we're going to take from the S domain this U of S, C, theta minus theta. And if we plug that back into our block diagram, we're going to get a new transfer function, which is now not only going to capture the motor itself, but it's also going to capture this controller. And then we'll see, based off of that transfer function, how can we choose the C to do certain things for our system. And that'll lead us to ideas of looking at pools of systems. And not only can they tell us stability, but they can also give us some insight as to how our system is going to respond. Right? Can we expect to see a lot of oscillations? Is there going to be a lot of tracking error? Right? How close are these two actually going to be to each other? Are there ways that we can compensate for that? And that sort of behavior is what we'll start looking at next time. And specifically, we'll be looking at pools of second order systems, because those have some good characteristics that we're generally interested in. All right, so we'll end there for today.